Black holes, the silent architects of the cosmos. They are invisible, unstoppable, and almost mythical in their power. For centuries, they've stood at the edge of human understanding, mysterious gateways where light itself disappears and time loses meaning. Unlike stars, which burn with life, or planets, which reflect it, black holes are defined by absence, a place where gravity reigns supreme and matter collapses beyond recognition. They are not just objects, they are phenomena, boundaries between what we know and what we cannot yet comprehend. At their heart lies the singularity, a region of infinite density where the familiar rules of space and time no longer apply. It is here that our greatest theories, Einstein's relativity and quantum physics, collide and fall apart. The roots of this mystery trace back to 1915, when Albert Einstein revealed his general theory of relativity. In it, gravity was no longer a force pulling on matter, it was the warping of spacetime itself. Soon after, in 1916, German physicist Karl Schwarzschild found a startling mathematical solution to Einstein's equations. A point so dense, its gravity would trap even light. At the time, this dark star was thought to be pure theory, a strange curiosity in mathematics. For decades, black holes remained an idea, unseen, unproven. But as telescopes grew sharper and instruments more sensitive, the shadows began to take shape. In the 1960s, astronomers discovered a star system named Cygnus X1. One bright blue star circled an invisible partner, an unseen object so massive that nothing known could explain its pull. The intense X-rays pouring from the system hinted that gas was being torn from the visible star, spiraling into an unseen abyss. It became one of the first real-world proofs of a black hole, a cosmic predator feeding on a stellar companion. Yet black holes are not simply destroyers. Paradoxically, they are also creators. Their gravity shapes galaxies, regulates star formation, and even stirs the interstellar medium, the gas and dust that form new suns and planets. At the heart of nearly every large galaxy lies a supermassive black hole, millions or even billions of times the mass of our Sun. Our own Milky Way is anchored by one, Sagittarius A*, quietly spinning in the darkness, its gravitational pull orchestrating the motion of stars like a conductor leading a cosmic symphony. Even though they are everywhere, black holes cannot be seen directly. No light escapes them. Instead, astronomers detect their presence by watching how matter behaves nearby. As gas and dust spiral inward, friction and gravity heat the material until it glows fiercely in X-rays, forming what is called an accretion disk. Around that glowing ring lies the event horizon, the point of no return. Anything crossing it, matter, light, even information, is lost to eternity. And beyond that? The singularity, where physics breaks down. Here, the density becomes infinite, and time itself may cease to exist as we understand it. One of the most extreme effects near a black hole is known as spaghettification. As an object falls inward, the difference in gravity between its top and bottom stretches it like a strand of pasta until it is torn apart at the atomic level. It's one of nature's most violent acts, yet also one of its most fascinating. For over a century, black holes remained invisible until 2019. That year, the Event Horizon Telescope, a worldwide network of radio observatories, achieved the impossible. It captured the first direct image of a black hole's shadow, the one at the center of galaxy M87, 55 million light-years away. The picture revealed a glowing ring of light encircling darkness, the outline of the event horizon itself. It was more than an image, it was a turning point in human history. For the first time, we had seen what was once only imagined. Surrounding that shadow lies the photon sphere, a region where light orbits the black hole, trapped in a never-ending dance. Inside that boundary lies the singularity, a place where space-time folds upon itself. Understanding this realm could unlock one of the greatest puzzles in science, the unification of relativity and quantum mechanics. Physicists have long believed that the universe hides its deepest truths in simplicity, that beneath all its chaos lies order, harmony, and pattern. String theory is perhaps the boldest expression of that belief. It proposes that everything, every particle, every photon, every bit of matter and energy, is not a point, but a vibration. A tiny loop of energy, endlessly oscillating. Each vibration plays a different note, and together, they compose the vast cosmic symphony we call reality. If this is true, then the universe is not built of bricks, it's woven from music. The frequency of these strings determines the nature of everything: gravity, light, quarks, electrons, all born from the same underlying song. Matter and energy become verses of a single cosmic melody. But this elegant theory also reveals a hidden architecture, extra dimensions beyond the three we move through and the one we call time. 10, perhaps 11 dimensions in all, curled up so tightly that we can't see or touch them. They may be smaller than atoms, existing in ways that stretch human imagination. And somewhere within those dimensions, the true nature of black holes, and perhaps even the birth of the universe, could finally be explained. Among the most haunting mysteries they raise is the black hole information paradox. When something falls into a black hole, a planet, a star, even a single photon, what happens to the information it carries? Does it vanish forever, erased by gravity's abyss? Einstein's general relativity says yes, nothing escapes. But quantum physics whispers otherwise, that information can never truly be destroyed. Resolving this paradox might unlock the long-sought theory of everything, uniting the laws of the very large and the very small. Yet, not all black holes are equal. Some rotate at staggering speeds, their spin described by the Kerr metric. As they turn, they drag spacetime itself around them, a phenomenon known as frame dragging. In these violent cosmic whirlpools, energy can be extracted from rotation itself, a process that could, one day, power civilizations beyond our imagination. The region outside such a spinning black hole, where space and time are pulled along, is called the ergosphere, a boundary between the possible and the impossible. Even more mysterious is the idea that black holes may not be endings at all, but gateways. The equations suggest that they might connect distant corners of the universe through tunnels in spacetime, wormholes, shortcuts across the cosmic sea. To some physicists, these bridges could even link parallel universes, offering glimpses into alternate realities that exist alongside our own. Though still unproven, the mathematics is tantalizing, the borderland between physics and dreams. Then came 2015, the year humanity heard the universe for the first time. The twin observatories, LIGO and Virgo, detected faint tremors rippling through spacetime, gravitational waves born from colliding black holes billions of years away. These waves confirmed one of Einstein's final predictions, proving that space itself can stretch, bend, and ripple like a living ocean. Each detection since has been a message from the past, a whisper from stars that died long before Earth existed. Every pulse carries the story of cataclysmic creation, where destruction births new order. From these cosmic collisions, galaxies grow and evolve. Black holes, once seen as monsters, are now understood as sculptors, engines of gravity that shape stars, stir galaxies, and recycle matter across eons. Without them, the universe would be silent, static, lifeless. They are both the wombs and the tombs of creation, the ultimate paradox of existence. And in studying them, we see a reflection of ourselves. Fragile beings drawn toward mystery, standing before the unknown, daring to ask questions even the universe struggles to answer. Through every telescope, every simulation, every spark of curiosity, humanity stretches a little farther into that darkness, not out of fear, but out of wonder. Because black holes remind us of something profound. That even in the deepest shadows, there is structure, motion, and meaning. They show us that endings are not truly ends, they are transformations. That within collapse, there is renewal. Within silence, there is music. And as our instruments grow sharper, we may one day peer into a black hole's heart, to see not destruction, but a window into the next chapter of cosmic evolution. In the end, black holes are not just astronomical objects. They are metaphors for existence itself, invisible yet powerful. Terrifying yet beautiful. Silent, yet speaking the language of the cosmos. They are the universe dreaming of itself, and through them, so are we.